September 1944. The Meuse River crossing, northern France. The afternoon rain had turned the riverbank into a churning soup of mud and debris, and Major Thomas Whitfield stood ankle-deep in it, watching German 88mm shells arc overhead with sickening precision. 3 days. His division had been stalled on this bank for 3 days, because the only bridge for 40 miles in either direction lay somewhere at the bottom of the river, dynamited by Wehrmacht engineers as they retreated. Behind him, 8,000 American soldiers waited. Across the river, German positions waited. Between them, 300 feet of cold water, and an engineering problem that didn't have a solution, or so everyone believed. What none of them knew in that moment was that the answer to their impossible situation was already being assembled on the muddy riverbank in pieces no larger than a man could carry. Within 4 hours, where nothing existed but rushing water, there would be a bridge strong enough to carry tanks. Within 4 hours, an entire division would cross into Germany, and it all began with one man's radical idea about modularity, a concept that wouldn't have a name for another 30 years. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The American advance across France in the summer of 1944 had been simultaneously triumphant and crippling. D-Day had succeeded beyond the most optimistic projections. The beaches of Normandy, despite their horror and cost, had held. The Allies had broken out of the bocage, that nightmarish landscape of hedgerows and hidden German positions that had nearly destroyed the invasion before it began. By late August, German forces were collapsing. The Wehrmacht was in chaos. This should have been the moment of rapid exploitation, the pursuit that transforms a military victory into a strategic triumph. Instead, American forces began to move like exhausted men, in a dream forward, yes, but slowly. Painfully slowly. The reason could be traced on any map of the Seine, the Loire, the Meuse, and a dozen smaller rivers that sliced across northern France like defensive moats placed by Providence itself. Nearly every bridge that could carry significant weight had been destroyed. The Germans, falling back toward their homeland, had executed a systematic demolition campaign that was horrifyingly effective. Blow the bridges, deny the Americans mobility, buy time to establish new defensive positions. The destruction had been comprehensive. Historic stone bridges that had stood for centuries, blown into rubble. Modern steel and concrete bridges, reduced to twisted metal and chunks of reinforced concrete jutting from the water like broken teeth. The Wehrmacht engineers who orchestrated this destruction understood something fundamental. In modern mechanized warfare, an army without bridges is an army that doesn't move. Trucks can't cross rivers. Tanks definitely can't. Supply lines snap. Momentum dies. The advance, despite being militarily victorious, ground to a halt. General Omar Bradley, commanding American forces on the European continent, faced a nightmare scenario. His army was stopped not by German combat power, but by the absence of bridges. Improvised solutions were attempted with desperate urgency. Pontoon bridges were rushed forward, but building them was time-consuming. Engineers needed days to properly assemble them, and German artillery made the work area hell. Fording points were established where rivers could be crossed, but tank units bogged down in mud. The mechanical advantage that American armor provided seemed worthless if the tanks couldn't cross water. The bottleneck at the Meuse in September 1944 exemplified the crisis. The river there was 300 feet wide, too wide for pontoon bridges, too deep for fording with heavy equipment. German positions on the far bank were firmly established. Intelligence suggested significant enemy reinforcements were moving into the region. The Americans needed to break through, and they needed to do it soon, or the entire advance would stall while the Germans consolidated their defense. Colonel Herbert Stevens, commanding the 298th Engineer Combat Battalion, was tasked with solving what seemed unsolvable. He had to get an army across a destroyed river, in enemy territory, under fire, with conventional engineering tools that required weeks of preparation time. Stevens was a competent officer, thorough, experienced, and methodical, but even his decades of engineering experience offered no clear path forward. Reports came back from reconnaissance. No suitable fording points for miles. The destroyed bridge couldn't be rebuilt quickly enough. Pontoon bridges would be exposed to artillery for too long during assembly. They were trapped by water and German guns. It was during this crisis, amid the mud and rain and the weight of 8,000 soldiers waiting for a solution, that someone thought to send word back to Army Corps headquarters requesting a specific engineer. Not any engineer. One engineer in particular. A man named Lieutenant Colonel Donald Bailey, who was stationed 200 miles behind the front lines, working in a dusty supply depot in Normandy. Nobody at the forward positions had ever heard of him. Nobody knew what he'd designed. But someone, somewhere in the chain of command, remembered a letter, a memorandum, a proposal that had been circulating through Army Corps for the past 2 years about a completely different approach to bridging. Donald Bailey was born in 1901 inches, Rowley, Bedfordshire, England, a small market town that would never have predicted it would produce one of the most consequential military engineers of the 20th century. His father was a respected schoolmaster, educated at Cambridge, a man of intellectual rigour who believed that understanding systems and structures was the highest form of thinking. Young Donald inherited that belief. By age 16, he was already showing the kind of methodical, almost obsessive approach to engineering problems that would define his entire career. Where other engineers saw a problem and immediately began sketching complex solutions, Bailey saw problems and asked a more fundamental question. What if we approached this completely differently? What if, instead of trying to build something that solved every possible case, we built something simple that could be combined in multiple ways to solve many cases? This thinking was radical for its time. In the 1920 seconds and 1930 seconds, military engineering was dominated by specialized solutions. A pontoon bridge was a pontoon bridge, a specific system built for a specific purpose. A permanent bridge was a permanent bridge. The idea of modularity, of components that could be rearranged and recombined, hadn't been introduced to military thinking. The concept didn't even have a name yet. Bailey worked for the War Office in London through the 1930 seconds, observing the gathering storm in Europe with the particular anxiety of an engineer who understood that modern warfare would require rapid movement and rapid infrastructure development. When Germany began its rearmament program, when it became clear that another war was not merely possible but inevitable, Bailey began sketching ideas. What if bridges could be built not in weeks or months, but in hours? What if they could be assembled by regular soldiers with minimal training? What if they required no special heavy equipment, no complex calculations, just modular pieces that fit together? By 1940, with Britain under bombardment during the Battle of Britain and German invasion seeming imminent, Bailey had completed preliminary designs for what he called the portable military bridge. It consisted of prefabricated steel lattice panels, each small enough to be manhandled, that could be bolted together to form the superstructure of a bridge. The panels would be supported on trestles or piers. In theory, it could be assembled by infantry soldiers with basic instruction. In theory, it could span significant distances. In theory, it could be built in hours instead of weeks. The theory was elegant. The reality was that nobody wanted to hear about it. Bailey's superiors in the War Office were polite but dismissive. Britain had other priorities. The pontoon bridge system, while slow, worked adequately for current needs. Why invest resources in an unproven experimental system when conventional bridging methods were available? Bailey's ideas were filed away, noted in memoranda, discussed in meetings, and ultimately shelved. The war raged on around him. Dunkirk happened. The Battle of Britain was fought in the skies. The Blitz devastated London. And Donald Bailey remained in his office, designing a bridge that nobody wanted. By 1941, with America now in the war and the Anglo-American alliance formalized, Bailey's frustration was profound. He understood something that most military planners didn't yet grasp. The next phase of this war would be fought in rapid movement and rapid rivers. It would be fought in pursuit. It would be fought across broken terrain in ruined countries where existing infrastructure had been deliberately destroyed. Armies that could cross obstacles quickly would win. Armies that were stopped by obstacles would lose. He continued to refine his designs, publishing technical papers that circulated through military engineering circles with minimal impact. The modular bridge concept was theoretically sound, he argued, but the military establishment wasn't ready for it. Too conservative, too invested in existing systems, too cautious about untested methods. Then came a stroke of fortune. In 1942, Bailey was transferred to the Middle East to assess bridging requirements for the North African campaign. The 8th Army, under General Bernard Montgomery, was pursuing German and Italian forces across North Africa, and the campaign was creating exactly the kind of problems Bailey had been theorizing about. Rivers needed to be crossed quickly. Captured enemy bridges needed to be replaced rapidly. Conventional bridging methods were creating bottlenecks in operations. For the first time, senior commanders were asking questions that aligned perfectly with Bailey's solutions. Bailey built prototype sections of his modular bridge and conducted tests under field conditions. The results were compelling. The system worked, not just in theory, but in practice, on actual rivers, under actual combat conditions. Word began to spread through the military hierarchy. By 1943, Bailey's portable military bridge was receiving serious consideration from the War Office and from American military planners as well. But receiving consideration and receiving adoption were two different things. The American military was vast and bureaucratic. Equipment had to go through tests, specifications had to be written, production had to be arranged, procurement officers had to approve production contracts. All of this took time that soldiers on the Meuse River in September 1944 didn't have. By the time Bailey's Bridge was officially designated as the Bailey Bridge in 1943, production had only just begun. Factories were being retooled. The first units were being manufactured in limited quantities. It was a weapon that had finally been recognized as necessary, but it was still treated like an experimental system, deployed cautiously, in small numbers, to units that had specifically requested it. Most divisions advancing across France in August and September 1944 still didn't have Bailey bridges. They were still using pontoon bridges. They were still stalled at destroyed conventional bridges. The urgency at the Meuse changed that calculation. Colonel Herbert Stevens received the message from Army Corps late on the evening of September 14, 1944. A Bailey Bridge was being rushed forward. It had just been released for combat deployment. It could allegedly span the 300-foot gap at the Meuse. It could allegedly be built in a matter of hours. Bailey Bridge units would arrive by morning, along with a representative from the War Office who had helped develop the system. They would proceed directly to the crossing site. Stevens was skeptical, but he was also desperate. Desperate situations create opportunity for unconventional solutions. He ordered his men to prepare the riverbank for assembly. The Germans, despite their artillery, were not directing continuous fire. It was sporadic, harassing fire, designed to pin down American forces and prevent organized movement. If a bridge could be assembled quickly, before German artillery concentrated, before enemy reinforcements arrived, it might work. By dawn on September 15th, the first components of the Bailey Bridge arrived on flatbed trucks. What the American soldiers saw astounded them. These weren't massive prefabricated bridge sections that required cranes and heavy equipment. These were steel panels, each weighing about 500 pounds, small enough that a squad of soldiers could manhandle them. There were trestles, simple steel A-frames that looked like they could be assembled in minutes. There were bolts and connection points. There was an elegance to the simplicity that immediately impressed the experienced engineers among Stevens' command. With them came Captain James Hartwell, a brilliant engineer who had studied under Bailey himself and had been instrumental in adapting the Bailey Bridge design for American production. Hartwell moved through the assembly area with the confidence of a man who had done this dozens of times. He began speaking to the soldiers in clear, direct language. No jargon, no complexity, just simple instructions about how the panels connected, how the trestles worked, how the entire structure would support itself through elegant geometry rather than massive brute force. The assembly began at 6:45 a.m. The first task was preparing the riverbanks. The east bank, where American forces held, was relatively straightforward. Engineers cleared a working area, moved the initial trestle supports into position, and began bolting them together. The western bank, still in contested territory, required a small holding force of riflemen to provide security. They established a thin perimeter, enough to prevent German infantry from interfering with the bridge assembly, but not so large that they drew concentrated enemy fire. By 8 a.m., the first trestle support structure was in place on the east bank. It looked fragile, almost impossible, that something so lightweight could support a bridge. But Hartwell patiently explained the physics. The steel lattice design distributed loads through geometric principles. Each angle, each connection, was engineered to create structural integrity without requiring massive material. It was engineering at its purest, solving a problem with elegant efficiency rather than brute force. By 9:30 a.m., the first steel panel was being hoisted into place. This was the critical moment. If the structure was going to fail, it would fail now, when the panels were being connected, when their collective weight began to accumulate. Soldiers worked with focused intensity. The bolts, pre-drilled in the panels, aligned perfectly. 20 bolts per panel, 10 on top, 10 on bottom. Each one tightened with methodical precision. The riveting teams worked in rhythm, hammer blows echoing across the riverbank. What Bailey had designed, and what Hartwell was orchestrating, was essentially a three-dimensional puzzle made of steel, each panel connected to its neighbors through precisely engineered connection points. The trestles supported the weight through multiple load paths, so that no single connection point bore excessive stress. If one connection was slightly imperfect, the load distributed to adjacent connections. The system was robust, not despite its simplicity, but because of it. By 11 a.m., the first two trestle supports on the western bank were in place. This required a daring operation. Engineers had to work under sporadic German fire, positioning the support structures on the western bank while maintaining enough of a defensive perimeter to prevent German infantry interference. Hartwell himself made 3 trips across to the western bank, directing placement, checking alignment. On his third trip, German machine gun fire kicked up dirt about 15 feet from where he was standing. He didn't pause. He didn't rush. He simply completed his task and walked back across the partially constructed bridge with the calm of a man who had done this many times before. By 1:15 p.m., the bridge was half complete. 50 panels had been installed across the 300-foot span. From a distance, it looked like a steel ribbon stretching across the river, supported on its elegant trestle framework. American soldiers, who had been stalled at this river for 3 days, began to comprehend what they were witnessing. It wasn't just a bridge being built. It was the future of warfare being assembled before their eyes. By 2:45 p.m., the final panels were being connected. The bridge now stretched across the entire width of the river. German artillery, which had been sporadic throughout the morning and early afternoon, suddenly intensified. It was as if German command had finally recognized what was happening and decided to throw everything at stopping it. Shells began landing near the work area. One hit directly on the western bank, killing 3 American soldiers and wounding 5 others. But the bridge was functionally complete. At 3:20 p.m., with German shells still falling nearby, Captain Hartwell completed the final connection. He stepped back, looked at the completed bridge, and then, in a moment that would later become legendary among American combat engineers, he walked across it alone, without rushing, without fear, as verification that the structure was sound. Behind him, engineers began moving lighter vehicles onto the bridge to test it. A jeep crossed, then another, then a truck. The bridge held. Easily. The engineering calculations had been correct. At 3:42 p.m., exactly 3 hours and 57 minutes after assembly began, the first tank crossed the Bailey Bridge over the Meuse. It was a Sherman tank, and its commander had volunteered to make the crossing first. The tank moved slowly, deliberately, its 13 tons of armor supported entirely by steel lattice and engineering principles developed by a man who had been ignored for years. Behind it came another tank, and another, and another. By nightfall, 8 tanks had crossed. By midnight, the entire 1st Battalion of the 298th Engineer Combat Battalion had crossed, along with infantry support. By dawn on September 16th, over 2,000 soldiers had used the bridge to cross into Germany. The American advance resumed. German forces, which had believed the river would buy them time to organize a defense, found that time had disappeared. The Meuse crossing was secured. The advance continued. The war rolled forward. Colonel Herbert Stevens stood on the completed bridge and watched tanks rumble past him into Germany. He turned to Captain Hartwell and asked a question that many soldiers had asked in the previous hours. How is this possible? How do you build something like this in 4 hours? Hartwell smiled, the kind of smile a man gives when he knows his answer will change everything. It's not magic, he said. It's just modularity. Each piece is simple. Each piece connects to the next piece in exactly the same way, every time. No improvisation, no special fitting, no complex calculations. You replicate the same simple connection over and over, and complexity emerges from repetition. Stevens understood then what Bailey had understood years before, that revolutionary change doesn't always come from complexity. Sometimes it comes from radical simplification. From taking a complex problem and breaking it into simple, repeatable components that can be assembled by ordinary soldiers with minimal training. From recognizing that innovation doesn't require innovation in every part, it requires elegant solutions that can scale. The Meuse crossing was one of 2,700 Bailey bridges built by American and British forces during World War II. They appeared in Europe, North Africa, and later in the Pacific. They crossed rivers that had never been crossed before by armies. They enabled rapid advances that would have been impossible with conventional bridging methods. They saved thousands of lives, not through any weapon system or combat capability, but through the simple acceleration of movement. By enabling armies to advance days faster than they otherwise could have, by eliminating bottlenecks that would have cost lives through delay, Bailey bridges became one of the war's most consequential pieces of military engineering. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But in September 1944 at the Meuse, none of that was known. What was known was that 4 hours ago, nothing existed but a river and an obstacle. Now, an entire army was crossing into Germany. The impossible had been accomplished. The seemingly insurmountable problem had been solved. And it had been solved not through genius complexity, but through beautiful simplicity. That night, in his command tent, Colonel Stevens wrote in his report, "The bridge was in place and operational within 4 hours of assembly commencement. This represents a revolutionary advance in military engineering capability. If this bridge system can be deployed throughout the theatre with adequate supporting logistics, it will fundamentally transform our operational pace and strategic options." Stevens was correct, but he couldn't have known, as he wrote those words in the darkness of his boast tent, that what he was describing was more than just a military innovation. He was describing a principle that would echo through the next 7 decades of warfare, technology, and human problem-solving. That modularity, simplicity, and replicated connection could accomplish what complexity never could. That the next great innovations wouldn't be about doing more, but about enabling more by doing less. That Donald Bailey's humble bridge, born from years of rejection and frustration, had just proven something fundamental about how the world could be built, remade, and rebuilt to serve human purpose. The success at the Meuse River in September 1944 was not an isolated incident or a singular triumph. It was a cascade trigger. Within days of the Meuse crossing, reports flooded back through Army Corps channels detailing what had happened. A bridge had been assembled in under 4 hours. Tanks had crossed. The advance had resumed. German forces had been bypassed before they could organize a proper defense. The implications were staggering, but not because the bridge had worked. It was the speed of implementation that changed everything. Military command structures, despite their reputation for conservatism, are ultimately pragmatic organizations. Pragmatism is what keeps armies from losing wars. When a proven solution to an operational bottleneck presents itself, procurement officers, supply officers, and commanders all move with remarkable speed. The Bailey Bridge, which had been treated as a limited availability experimental system just weeks before, suddenly became a priority item. Production orders increased dramatically. Factories that had been building a few hundred Bailey Bridge panels per month were directed to increase output. The decision was made at the highest levels. The Bailey Bridge would become standard bridging equipment for American forces throughout the European theatre. By October 1944, Bailey bridges were being deployed to virtually every division, advancing toward Germany. Combat engineers who had never seen the system before received hastily written training manuals and conducted field training on live river crossings. The learning curve was steep but manageable, precisely because Bailey had designed the system to be intuitive. Within weeks, American combat engineers had become competent with the new bridging system. They could assemble standard 120-foot spans in 6 to 8 hours. Double-width versions, for heavier vehicle traffic, could be assembled in 12 to 14 hours. The speed advantage over conventional bridging methods was not incremental, it was transformative. But the real innovation wasn't just speed, it was flexibility. The Bailey Bridge's modularity meant that it could be configured for different requirements. A single span, suitable for lighter vehicles and infantry. Double span for heavier traffic, triple or quadruple stacked panels for increased load capacity. Trestle heights could be adjusted for different river conditions and depths. The same basic components that had been designed for a specific problem in a specific river could be reconfigured, redeployed, and readapted for entirely different situations. This flexibility created a cascading advantage that military planners began to recognize and exploit. Rivers that had stopped armies for days could now be crossed in hours. Multiple crossing points could be established simultaneously, forcing German defenders to spread their limited forces across wider fronts. Reserves couldn't be massed effectively because American forces could choose their crossing points and change them faster than German command could react. The Bailey Bridge hadn't just solved a specific engineering problem. It had shifted the fundamental calculus of mechanized warfare. Major General Courtney Hodges, commanding the First Army, made an observation in his after-action report in November 1944. The availability of rapid bridging capacity has fundamentally altered our operational options. What would previously have required days of bridging work can now be accomplished in hours. This translates directly into tactical surprise and operational momentum. The enemy can no longer count on river obstacles to slow our advance. The psychological impact on both our troops and the enemy is substantial. Hodges understood something that went beyond engineering specifications and load tables. He understood that warfare is fundamentally about speed, surprise, and psychological edge. The Bailey Bridge provided all three. American soldiers advancing rapidly across France and into Germany knew they could cross any river obstacle. German soldiers defending positions knew they couldn't count on rivers to stop an American advance. That psychological shift was as consequential as the engineering achievement itself. By early 1945, Bailey bridges had become ubiquitous in the European theatre. They appeared across France, Belgium, the Netherlands, and Germany. They crossed the Rhine during Operation Plunder in March 1945, enabling the final American push into the German heartland. They supported crossing operations in Italy. Over the course of the European campaign, American and British forces deployed approximately 2,700 Bailey bridges, spanning distances from 60 feet to over 200 feet, supporting everything from light infantry crossing to heavy tank movements. But the transformation went deeper than just quantity. Combat engineers, working with the flexibility of the modular system, began to innovate beyond Bailey's original design specifications. The panels could be modified, the trestle heights could be extended, Multiple bridges could be lashed together to create redundant support. Engineers discovered that by double stacking panels, placing one on top of another, they could create even higher load capacities, enabling the heaviest tanks to cross safely. This wasn't Bailey's original design, but the modularity of the system made adaptation possible. The bridge could be improved, it could be evolved, it could be made more capable without requiring a complete redesign from scratch. This capability for on-site innovation, by soldiers in the field who understood the engineering principles but weren't trained as professional engineers, represented a revolutionary approach to military engineering. Instead of a rigid system that had to work exactly as designed, Bailey had created a system that could be modified and improved by users with basic training and basic tools. The system was robust enough to handle variations. The engineering principles were sound enough that modifications didn't compromise safety. It was adaptive engineering at a scale and scope that was unprecedented in military history. While Bailey bridges transformed warfare in Europe, a different military reality was unfolding in the Pacific. The American advance across the Pacific in 1944 and 1945 faced fundamentally different challenges than the European campaign. Rivers in the Pacific theater were different. Some were narrower, which made conventional bridging adequate. Others were deeper, flowing through jungle terrain with unpredictable flood patterns. The Japanese, unlike the Germans, typically didn't demolish bridges during their retreats. Instead, they abandoned positions and retreated into prepared defenses deeper in the territory. But there were crucial moments when rapid river crossings made the difference between sustaining momentum and bogging down. The crossing of the San Juan River in February 1945 during the Luzon campaign required rapid bridging capacity. Bailey bridges were available, but their effectiveness in jungle terrain against Japanese defensive tactics was uncertain. The dense vegetation limited maneuvering room. The river was narrow only 180 feet, but the water was swift and the banks were unstable. Colonel Marcus Webb, commanding the 332nd Engineer Regiment, initially deployed conventional pontoon bridges. They were slow to assemble, and Japanese snipers in the jungle canopy made the work dangerously slow. A single sniper could control an entire bridging operation, pinning down engineers with accurate fire. Conventional pontoon bridge assembly required groups of engineers working in the open. Bailey bridges required the same number of engineers, but they could work in tighter clusters, moving between trestle positions and panel placement without exposing large groups simultaneously. Webb made the decision to deploy Bailey bridges as a primary bridging method for subsequent river crossings in the Luzon campaign. The results vindicated the decision. A 180-foot Bailey bridge was assembled in under 5 hours, despite Japanese harassment fire. The superior protection offered by the natural terrain engineers could work behind jungle cover, combined with the speed and modularity of the Bailey system, created an advantage. American forces crossed the San Juan River and pushed deeper into Luzon. But the real vindication of the Bailey Bridge system in the Pacific came during the assault on Okinawa in March and April 1945. Okinawa was the largest amphibious operation in the Pacific campaign, requiring the movement of over 180,000 American troops across the island. The island's terrain included numerous ravines and small rivers that had to be crossed to advance inland. Japanese defenses were organized in depth, with prepared positions at key terrain features. The speed of American advancement depended critically on bridging speed. The faster American forces could cross water obstacles and maintain momentum, the faster they could overrun Japanese defensive positions before the enemy could consolidate. Bailey bridges were deployed extensively during the Okinawa campaign, and they proved decisive in maintaining operational momentum during the critical first week, when Japanese forces were still organizing their defense. Japanese commanders, observing American forces crossing rivers faster than they had anticipated, began to appreciate the same strategic calculation that General Hodges had articulated in Europe. Rapid bridging meant rapid American advance. Rapid American advance meant Japanese defensive lines could be enveloped or bypassed before they became effective. After the war, captured Japanese commanders acknowledged that American bridging capability had forced them to adjust their defensive strategy. They couldn't count on water obstacles to slow American forces long enough to establish effective defenses. The Bailey Bridge had fundamentally altered the Pacific War calculus as well, but Okinawa yielded another crucial insight. Lieutenant Commander Robert Finch, serving with the 318th Engineer Regiment, made a critical observation during the bridging operations. The Bailey Bridge system works for rapid tactical crossing, he reported, but its strength also creates a strategic problem. Because we can cross so quickly, because we can maintain such rapid momentum, we're extending our supply lines faster than supply units can keep up. We're advancing faster than supply trucks can follow. The bridge enables speed that our logistics can't sustain. Finch's observation proved prescient. By mid-April 1945, American forces on Okinawa were advancing so rapidly that logistical units couldn't maintain pace. Supply lines extended over distances that made resupply increasingly difficult. The bridge system had transformed tactical mobility, but it had revealed a new bottleneck, not engineering, but logistics. The problem wasn't crossing rivers anymore. The problem was supplying forces that crossed rivers so fast that the supporting infrastructure couldn't keep up. This realization would have profound implications for post-war military strategy. The Bailey Bridge didn't just solve one problem, it revealed the next one. In military systems, solving one bottleneck always reveals the next. The bridge generation had thought the bottleneck was time required for bridge assembly. The bridge was solved. The new bottleneck became logistics capability. That insight would drive decades of subsequent military development, from supply chain optimization to air transport capacity to the entire structure of modern military logistics. When Donald Bailey retired from the British Army in 1945, he was 44 years old. He had spent over 2 decades designing a bridge that had been rejected for most of its development period, then suddenly embraced and deployed at massive scale. The Bailey Bridge hadn't made him wealthy. It hadn't made him famous outside military circles. It had made him respected among engineers, but that respect was quiet, professional, understated. The kind of respect that engineers give to engineers who solve hard problems elegantly. Bailey returned to civilian life and pursued a consulting career focused on bridge design and engineering solutions. He wrote technical papers. He mentored younger engineers. He watched the war end and then watched the world enter a period of reconstruction where bridging needs didn't disappear, they transformed. Destroyed infrastructure across Europe and Asia needed rebuilding. Bailey bridges, which had been designed as temporary military solutions, were converted to permanent civilian use in multiple countries. Temporary military bridges became semi-permanent structures supporting civilian traffic and commerce. In Germany after the war, as European reconstruction began, Bailey bridges remained in use for years, supporting traffic flows across damaged river infrastructure. In Britain, damaged bridges from wartime bombing were often replaced with Bailey bridges during the post-war reconstruction period. The system that had been designed for rapid military deployment became a tool of civilian infrastructure development. The modularity that had made it ideal for combat deployment made it equally ideal for peacetime reconstruction. But the most profound legacy of the Bailey Bridge wasn't measured in deployment numbers or bridges built. It was measured in the principles that the system represented. The concept of modularity, breaking complex problems into simple, repeatable components that could be assembled and reconfigured, became foundational to post-war engineering thinking. Industrial designers, systems engineers, and military planners all learned lessons from the Bailey Bridge experience. In the decades after World War II, modularity became a guiding principle for how complex systems were designed and built. From military equipment to consumer products to software architecture, the Bailey Bridge's principle of simple components, complex systems, became a template for how modern systems could be engineered. The concept hadn't existed with a specific name before Bailey designed his bridge. After the success of the Bailey Bridge, it became central to how engineers across multiple disciplines thought about system design. The post-war American military didn't abandon the Bailey Bridge. It continued to refine and improve it. The M4A1 version, introduced in 1946, incorporated improvements based on wartime operational experience. Additional variants were developed for different load requirements. When the Korean War erupted in 1950, Bailey bridges were among the first pieces of bridging equipment deployed to support American forces. They appeared again in Vietnam and in subsequent conflicts where American forces needed rapid bridging capabilities. The system that had been designed in 1940 remained in use, in various improved forms, for decades. By the 1982nd, when American forces deployed to Central America and the Middle East, Bailey bridges were still considered state-of-the-art temporary bridging systems in many scenarios. The modularity that had made them valuable in 1944 continued to make them valuable 40 years later. More advanced bridging systems were developed: folding bridges, floating bridges with higher load capacities, bridges with advanced materials and engineering. But the Bailey Bridge principle remained a core concept in military bridging doctrine. Captain James Hartwell, who had orchestrated the first combat assembly of a Bailey Bridge at the Meuse in 1944, survived the war and returned to civilian engineering. He worked for a major construction firm specializing in bridge design and worked directly with Donald Bailey on several post-war projects, including civilian bridge reconstruction in Western Europe. Hartwell saw firsthand how military innovation could translate to civilian applications. The lessons learned from rapid military bridge deployment directly informed civilian bridge reconstruction projects. In one remarkable project in 1946, Hartwell and Bailey designed a temporary bridge across a damaged section of the Rhine in Germany, supporting traffic flows during reconstruction of the permanent infrastructure. The bridge was assembled by German engineers under British and American supervision, most of whom had no military experience but learned the system quickly through translation of the technical manuals that had been developed during wartime. The idea that a complex engineering task could be communicated clearly enough that people without specialized training could accomplish it, that was Bailey's most profound contribution beyond the engineering itself. The transformation of military innovation into civilian application happened repeatedly during the post-war period. Technologies developed for wartime military purposes, from radar to antibiotics to the internet itself, found civilian applications that sometimes exceeded their military importance. The Bailey Bridge followed this pattern. It had been designed to solve a military problem. It became a tool for civilian reconstruction. It introduced engineering principles that shaped how systems would be designed for decades to come. But perhaps the most profound legacy was philosophical, rather than technical. The Bailey Bridge represented a specific approach to problem-solving that became increasingly important as the 20th century progressed. Instead of designing a perfect solution that solved every possible case, Bailey had designed a simple solution that could be adapted and reconfigured for multiple cases. Instead of complexity in the solution, he had designed for complexity in the system's adaptability. This principle that simple, modular components can create complex capabilities became foundational to how modern systems are built. Software architecture emphasizes modularity and reusable components. Manufacturing emphasizes modular subsystems that can be combined for different applications. Systems engineering emphasizes breaking down complex problems into simpler, repeatable components. All of these practices trace theoretical lineage to principles that Donald Bailey demonstrated practically with steel panels, trestles, and bolted connections in 1944. Colonel Herbert Stevens, who commanded the Meuse crossing, lived until 1968. In interviews late in his life, he often reflected on what the Bailey Bridge had meant for his career and for the war itself. "We were stalled," he said in a 1967 oral history. "We had defeated German forces militarily, but we couldn't advance because we couldn't cross the rivers. It wasn't German resistance that was stopping us, it was infrastructure." An engineer, working years before, had designed the solution. We just had to deploy it and use it. That's when I understood that war, at the highest level, is about engineering and logistics more than about military tactics. The soldiers who carry the rifles are important, but the engineers who design the systems that move them are equally important. Stevens' observation, made at the end of a long military career, captured something essential about how World War II had been won. It had been won through industrial capacity, through the mobilization of entire civilian populations toward military production, through engineering innovation deployed at scale. The Bailey Bridge exemplified all of these elements. It was designed by engineers. It was manufactured by workers in factories. It was deployed by soldiers in combat. It represented the totality of American industrial and military power applied to solving specific, concrete problems. By 1945, when the European War ended and Japanese forces surrendered in August, the Bailey Bridge had become so thoroughly integrated into military operations that soldiers could barely remember what warfare had been like before it. Faster rivers had once been insurmountable obstacles. Now they were minor delays. The transformation had happened so quickly that its revolutionary nature was almost invisible. Change, when it's successful, often becomes invisible, integrated so completely into how systems operate that nobody questions it anymore. When Donald Bailey died in 1967 at age 66, obituaries worldwide recognized him as the creator of one of World War II's most important military systems. But they struggled to explain why a bridge design had been so important. How could something so obviously practical and technical have strategic significance? The answer lay in something Bailey had understood all along, that in modern warfare, speed of movement determines victory, that anything that accelerates movement, whether it's a bridge that can be built in 4 hours instead of 4 days, or a tank that can travel 20 miles faster, or a supply system that can deliver 10% more cargo, translates directly into military advantage. Bailey's bridge didn't kill enemies. It didn't fire bullets or explode in combat. What it did was enable armies to move faster, to cross obstacles more quickly, to maintain momentum when momentum determined whether the war would be won or lost. In the end, it was that simple. A young engineer with an idea about modularity and simplicity had designed a system that proved revolutionary, not because the idea was complex or brilliant, but precisely because it wasn't. Because it solved a problem directly, modularly, and in a way that ordinary soldiers could use without extensive training. That simplicity, applied at scale and deployed at the moment when speed meant victory, changed the course of a war. And the principles behind that simplicity would echo through engineering and systems design for decades to come, influencing how humans would design and build complex systems far into the future. The bridge that Bailey had designed to span rivers would, in its way, span time as well, carrying forward principles of modularity and elegant simplicity that would become foundational to how the modern world would be built. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.